this is the Charles Hatchett Award winner 2020. Professor Manish Chhowalla, congratulations for this great goal. You are Professor of Materials Science, University of Cambridge, and you are bringing to us, you can see that right here, dear audience, the ultra-high current density niobium disulfide catalyst for hydrogen evolution. This is a big word, and I'm really looking forward for your award lecture for the next 20 minutes. The stage is yours.
Thanks very much, Silke. And I'd also like to thank Robson for giving a very nice introduction to the field of hydrogen in the broader context. It saves me a lot of background slides to present. And also thank you, CBBM, for this very nice award. So as Silke said, I'll talk about ultra-high current density niobium disulfide catalyst for hydrogen evolution reaction that we've developed in my laboratory. There are many people that have contributed to this work, and I'll mention a few of them towards the end. My name is Manish Chhowalla, and as Silke said, I work at the University of Cambridge. If you'd like to get in touch with me, you can contact me via email here or my Twitter handle. So niobium disulfide belongs to a family of, just get rid of this, belongs to a family of materials called the transition metal Dicholcognites, and they're shown here. TMDs have a generalized formula of MX2, where M is a transition metal, any metal from group 4 to group 10, and chalcogens are these sulfur, selenium, and tellurium atoms. And by combining the transition metals and the chalcogens, we're able to make up to 40 different compounds. And by rationally selecting the transition metal and the chalcogens, we can obtain a whole variety of different properties that we desire. In addition to the chemistry, we can also tune their structural phases. So these TMDs often occur in the 2H phase or the 3R phase that Robson mentioned, and also the 1T phase. The 2H phase tends to be semiconducting or insulating, while the 1T phase in the octahedral configuration tends to be metallic. And it's these metallic phases that are quite interesting for electrochemistry and catalysis and energy storage and so forth. The other important thing to note is that these TMD compounds with the MX2 formula comprising of these group 4 to 10 transition metals and chalcogens are in fact layered compounds. What this means is that they have a structure that's similar to graphite with strong in-plane bonding and weak interlayer bonding. And what this allows us to do is to go from a three-dimensional solid to a single sheet of these materials to what's referred to as a two-dimensional solid. So when we isolate a single sheet, it becomes two-dimensional because the absence of Z direction, there's no Z direction in these atomically thin nanosheets. And these two-dimensional materials are very interesting for many different applications, electronics, optical, but I'll talk about their very interesting electrocatalytic properties. So these materials have been widely studied for the hydrogen evolution reaction. The main reason for this is because they give good activity, but they're also earth abundant and inexpensive relative to platinum. The field was initiated by a report from Jaramillo et al. From Stanford. And what they did was they grew these clusters of molybdenum disulfide on single crystal gold. And when measuring the HER reaction from them, they found that the edges of these clusters are catalytically active. And the reason why the edges are active is because the molybdenum atom is exposed at the edges, and also because the edges are metallic. And so there was a huge amount of effort to try to increase the concentration of edges in as-grown molybdenum disulfide to improve the catalytic performance. However, the main drawback of these semiconducting 2H crystals that Jaramillo et al. Grew was that the basal plane, where majority of the atoms are located, are catalytically inactive. And so, as Robson also mentioned, that there has been a lot of effort to increase or facilitate electron transport in these materials so that electrons can reach the active site and the reaction can occur. And this becomes an important parameter that we've been able to optimize in our niobium disulfide catalyst. Strain, we reported that strain is a variable that can be tuned to tune the free energy of the reaction. In 2013, we showed that the metallic phases of these TMD materials, the 1T phase in particular of MOS2, is extremely good catalyst for the HER reaction. Furthermore, we showed that the activity of the metallic phase was not isolated just at the edges. In fact, the basal plane was also catalytically active. And this led to a significant enhancement in catalytic activity because now you have more active sites on the basal plane, mitigating the HER reaction. We've also shown that the coupling of the catalyst between with the catalyst support, typically carbon, is also very important in optimizing the performance. And we've also studied defects. And so our work on metallic phases of MOS2 and other TMDs for HER has led to other studies. But here's just a summary of one of our initial reports published in 2013. This is with MOS2. We also published a similar study with tungsten disulfide, where we showed that this 1T phase, which is the metallic phase, is catalytically more active than the 2H phase, where only the edges are active. And you can see that it's not as active as the platinum, but the overpotentials that we obtained for the 1T phase of tungsten disulfide and MOS2, the performance metrics are not so bad. That is, we require only an 80 millivolt overpotential for tungsten disulfide and a slightly higher overpotential for the 1T phase. The Tafel slope, which is shown here, is an indication of the reaction kinetics. And one can see that the Tafel slope of the 1T phase MOS2 is quite low. And for comparison, the Tafel slope for platinum is on the order of 30 millivolt per decade. So we can see that we can really improve the catalytic performance quite dramatically by using metallic TMD compounds. Of course, this 150 millivolts might seem large, but this is well within the open circuit voltage of a solar cell. So we can use a renewable source to generate our potential to drive the catalytic reaction. And so our initial work from 2013 has inspired several studies. So I'll just highlight a couple. Robson already mentioned one of them. But this one is from the Yanfang Zhang group at Peking University. And what they've done is they're very good at growing these metallic TMDs like tantalum disulfide on gold single crystals. And they found that these tantalum disulfide crystals are extremely good for HER catalysis. They find overpotential values that are very low. This black curve is the reference curve for platinum. And you can see that the overpotential is very close to that of platinum. Furthermore, they find that the Tafel slopes of these tantalum disulfide catalysts is comparable to platinum. So the reaction kinetics in these metallic TMDs is very close to that of platinum. They've done calculations to show that in the case of tantalum disulfide, not only the edges, but also the basal planes are catalytically active. That is, their free energy is close to the thermoneutral value, which is what you desire for HER reaction. And also the sulfur edges are catalytically active. So there are multiple sort of active sites located within tantalum disulfide that gives these excellent HER characteristics. And again, Robson mentioned this, but one sort of curious thing about these materials is that they improve with cycling. That is, this is the initial HER performance, but as you cycle up to 5,000 cycles, you can see that both the overpotential and the Tafel slope decrease quite dramatically. So another example of these metallic TMDs acting as a very good catalyst for HER is from the Jacobson group from Rice University in Houston, Texas. So they've studied materials like niobium disulfide and also tantalum disulfide. And what they again show is that it's possible to have very low overpotentials for the HER reaction and also Tafel slopes down that are close to that of platinum. And once again, what they find is that in the case of niobium disulfide, there is a kind of a conditioning process where the material actually gets better. The number of active sites improves with the number of cycles. So in this diagram, they show that after just 2 cycles, they have a very large Tafel slope of around 300 millivolt per decade. But after 5,000 cycles, the Tafel slope decreases to 37 millivolt per decade. So there is this enhancement of instability and performance with the number of cycles, which is quite useful for catalysis. However, the main problem that sort of plagued the metallic TMD or just TMD for HER research is this very low current densities that are achieved. So typical sort of current densities that are achieved with these TMDs are in the order of tens, if not hundreds of milliamps per centimeter squared. And for real electrolyzers, as Robson mentioned, for practical electrolyzers, we'd require current densities on the order of amps per centimeter squared. So we wanted to see if there was a rational way that we could address this issue of low current density with TMDs and achieve current densities that were more practical. So we went back to the literature and we looked at various different phases of niobium disulfide. So the 2H and the 3R phases are well known. These are for layered materials where, again, you have your single layer and a van der Waals gap between the layers. And this inherently limits the overall current density because, as Robson mentioned in his first presentation, that these van der Waals gaps act as effectively resistors in series, which decreases the efficiency of electronic transport. And the same sort of thing happens in the 3R phase. So while the thermodynamics of these phases is good, the reaction kinetics and charge transport is limited, which lowers the overall current density. So we synthesized this phase of niobium with excess amount of niobium. So the stoichiometry now is more like NB 1.35S2. This is because we've incorporated now niobium between these layers. So now these layers are strongly coupled. And so now we can have a good electronic transport in the Z direction as well as the X and Y direction. So when we can do cross-sectional transmission electron microscopy to look at the electronic structure. And what we find is quite curious. It turns out that in the case of niobium disulfide, the metallic 2H phase is preferred at very low thicknesses. And as you go to higher thicknesses, we obtained what is referred to as the rhombohedral phase. And in our calculations, we found that the metallic 2H phase of this excess niobium disulfide material is better for catalytic performance. So the kinetics of growth here are also interesting, but I won't talk about that here. When we characterize the as-grown material, particularly at low thickness values, where we have the 2H phase of this excess niobium disulfide material, what we find is that we have our individual layers, but between the layers, we can find atoms of niobium. And this phase is not new. In fact, it's quite old. It was first synthesized and proposed in 1960 in a paper in Nature. But since then, it's been largely ignored. But it turns out to be very useful for catalysis, as I said, because we can now have increased conductivity, electrical conductivity in the Z direction as well as the X and Y direction, while retaining the thermodynamics of niobium disulfide as a catalyst. So here's just a summary of some of those results. So again, this is just a more colorful image of our cross-sectional transmission electron microscopy image. And this graph here shows what's called the Z contrast analysis. And from that, we can show that there is intercalated, or not, there is a niobium atom sitting in between the layers. And you can see that each layer has this niobium atom present. And when we do the electrical measurements, we find the material to be highly conducting, both in the XY plane, but also in the Z direction, with conductivity values that are quite high for these metallic TMDs. And Robson already showed this result, but our calculations, our first principle calculations, show that both the 3H and the 3R and the 2H phases have good thermodynamics, but the 2H phase is closer to the thermoneutral condition, which is what you desire for the HER, good HER performance. But we can see that adding this excess niobium really introduces good thermodynamics so that the reaction can be facilitated. The difference between the energy states is where this, if the surface is sulfur terminated, we see that the free energy is quite high, but when it's niobium terminated, the free energy is close to zero. And this indicates that, in fact, it's the niobium that is the crucial active site for HER in these materials. So these are the polarization curves from the catalysis reactions, where I've plotted the current density as a function of the potential, where the potential is with respect to some reference electrode. These two plots are exactly the same. The vertical axis here only goes up to 100 milliamps per centimeter squared. So this is just a very small region of this plot that's been expanded. But if we look at the left-hand side curves, what we can see is a comparison of the polarization or the catalytic activity of all the different types of TMD materials that we've studied in my group, as well as platinum for comparison. And we see that platinum, of course, is a very good catalyst. But the interesting thing about this metallic excess niobium phase shown in green here is that we're able to achieve very high current densities in these materials, so that at 400 millivolts over potential, we can get 1, 2, 3 amps per centimeter squared of current density. And the rate of hydrogen evolution reaches 300 liters per centimeter squared per hour in these catalysts. We can also examine the reaction kinetics by looking at the Tafel slope, and we can see that we achieve a Tafel slope around 40 millivolt per decade at low current density and low potentials. It increases slightly at higher current density and higher over potential. And the reason for this is the diffusion kinetics of the electrolyte have not been optimized yet. And the turnover frequency values, that is how active an active site turns over the reaction, is also quite good relative to other types of catalytic materials in the literature. So taking all of these things into account, we wanted to demonstrate a proof of concept device, so a very crude electrolyzer where we used our niobium disulfide as a cathode and a platinum as our anode. Again, this is in no way optimization. We just wanted to see if we could replicate the large current density values that we obtain in our polarization curves into an actual device. So we can see that in this case, we've achieved very high current densities. In this inset, we show the percent change of the overpotential as a function of time, so running the same reaction over 100 hours. We've also done it for thousands of cycles, and in fact, it's very stable. And the electrolyzer output characteristics are shown here, and we see that we're able to achieve close to an amp per centimeter squared at 2 volts for this very crude electrolyzer without any optimization. So this suggests that at least this excess niobium disulfide material and its catalytic properties are good, but it's also quite robust in terms of evolving a large amount of hydrogen. Okay, so with that, I'll conclude my talk, but not without stating the most important part of the talk, which is acknowledging the people who did the actual work. And in particular, I'd like to acknowledge Dr. June Yang. She's a postdoc in my group, and she led this study. She did all the electrochemical and catalysis experiments, as well as characterization of the material. She worked very closely with Abdul Rahman Mohammed, who was a visitor from Malaysia, spent 2 years in my lab, and he synthesized the excess niobium disulfide material using chemical vapor deposition directly on carbon supports, which I think is also quite important technologically. And so they deserve all the credit for this work. I'd also like to acknowledge very important collaborators for the work. Dr. Elton Santos, who's now at the University of Edinburgh. Elton really provided the theoretical guidance for this work, which is enormously helpful towards optimization of our catalyst. Also, Professor Huyong Jung from Ulsan National Institute of Science and Technology in South Korea, who, with his team, performed the high-resolution TEM images that I presented. Absolutely beautiful, and a picture is worth 1,000 words. So if you can see the structure with atomic resolution, it makes things a lot easier. And finally, I'd really like to thank CMMB for sponsoring this award. I think it's really helpful to have an industrial company that is interested in our work, and also the Charles Hatchett 2020 panel for deeming that our work is worthy of this very prestigious award. We're really humbled and honored to receive the team. The entire team is honored and humbled to receive the Charles Hatchett Award. So thank you very much for your attention, and I'm happy to take any questions.